Uh, Hello, everybody. Good afternoon. We are back to our webinars. Today, we have the pleasure to receive Nuno Sepúlveda to give us this talk with the title "The Three Sigma Rule to Define Antibody Positivity. Is it a beauty or a beast?" Nuno is professor at the in Warsaw University of Technology. He has his bachelor and his master's degrees in applied mathematics and computation from the Technical University of Lisbon. He developed mathematical theories of the adaptive immune systems in his PhD project in the University of Oporto in Portugal. Nuno, once again, I would like to thank you for your kindness to come here today and giving us this talk. Please take the words. Feel free to talk.
Okay, First of all, thank you for having me, and thank you for the invitation. I hope this presentation you will find it useful for your future career, and you find this topic fascinating as I do. I don't think this is a very advanced topic, but I think comes to the basics of statistical inference, and I think sometimes we lose track of this basic knowledge of statistical inference, and we just keep on going doing the same stuff, and we don't stop to think what actually we do. So like Michelle said, the presentation is entitled "The Three Sigma Rule: Is it a beauty or a beast in serology data analysis?" And probably you know a little bit about serology. Serology is a fancy word for antibodies, okay? And antibodies became a little bit, popular with the pandemics. And I just bring you, some motivation for this talk. Um, so here in this slide, I took it from this diagram from the CDC website, so the Center for Disease Control of USA, where they talk about serology applied to the COVID-19, or actually more precise, antibodies against SARS-CoV-2. Okay, so mostly what just for the basic knowledge is that when someone is infected by a pathogen, in this case SARS-CoV-2, your body will react to that infection, and that reaction usually is done in terms of these antibodies. Antibodies are like these molecules or these proteins in this Y shape, okay? And the basic idea of serology applied to epidemiology is that when you take an individual from the population, and if this individual had the infection, that individual will have some detectable levels of antibodies, okay? And then that person was previously infected. So the main objective of what we call seroepidemiological surveys is to estimate the percentage of individuals in a population who have antibodies to an infection agent. And we call this percentage or proportion, we call it seroprevalence, okay? So the basic idea is that you screen for the antibodies from blood samples of individuals, and then you have to, and you need to know who are the individuals that have those antibodies. Technically speaking, the lab assays, actually, they usually don't give you like in this, in this like this little, I don't know, it's like a losangle, no, I don't know. That actually you have these teardrops, and in red they are the seropositive individuals, and in gray they are the seronegative individuals. So actually the lab assays don't provide you the data like this, okay? And so the antibody data that is actually intrinsic quantitative. And I'm just showing you here two examples of antibodies against the S1 protein of the coronavirus, SARS-CoV-2, okay? And here you see that the antibody values, they are continuous, okay? So this is for antibodies of class M, which means that antibodies of, of current infection. So these antibodies are produced, in the first days of the infection. And then you have what we called IgG antibodies. So the antibodies that actually are produced, after some time of the infection, and they are the basis of the, immunological memory. So which is in the basis of vaccine development. Okay. So this is this is the data. So the question is, by looking at these two plots, actually, where are you going to say that who are actually the seropositive individuals? So you have a continuous antibody values, and the question is, who are actually seropositive individuals? And now it's important to highlight something here in terms of the lab technique. So these antibody values, actually, they are not exactly antibody values. So what the lab assays are detecting is a light that usually is emitted by a dye that binds to the antibodies. Okay, because we live in a world without light, we don't live in a world without light. The machine that reads the light intensity coming from a sample, there's always some light coming in. So this light is correlated with these antibody values. So that's why you always have values here. So the basic idea to answer this question is to thinking about a cutoff that you put in these distributions, okay? And so I just put it here. And it's not obvious. It's maybe on the, on the plot on the right-hand side, it's much, plausible, the cutoff being there. The other one, it's not so, it's not so clear that you are going to have like a cutoff that divides into the population into antibody-negative and antibody-positive individuals, okay? So what are the approaches to determine this cutoff? And this is kind of like what most of the people do in any research on any infectious disease. So we have two ways of tackling this problem. One is to use an unknown seronegative population. In the case of COVID-19, so what they did is to use pre-pandemic blood samples, and then they screened for the antibodies against this corona protein, okay? The other approach is to use the data that this data set, exactly like this, and actually you fit a mixture model. And in this case, the mixture model, it's going to assume that you're going to have at least two latent populations, okay? One is the seronegative and the other one is seropositive. You can make things a little bit more complicated. So you can have antibody positive at the different levels. But for now, for the sake of for the argument, you're just going to assume that you can have a mixture model based on two components. And for the sake of statistical simplicity, you assume that each component of this mixture is actually modeled by a normal distribution, okay? So when you determine the seronegative population in these two approaches, then you apply this 3 sigma rule to determine this cutoff. And what is actually this 3 sigma rule? Probably you already have an intuition for this. So the 3 sigma rule tells you something like this. You have the mean of the antibody negative population and the standard deviation of that same population, okay? So what you're going to say is that the seronegative population will be classified as such if the antibody values are below the mean plus times 3 times the standard deviation, okay? And you can consider seropositive individuals otherwise, okay? So actually you're picking up the extreme values of the extreme values of the hypothetical seronegative population, okay? Now, if you think about this the 3 sigma rule, it's highly linked to the normal distribution. Okay, so when actually you use the mean plus 3 times the standard deviation of the normal distribution, and you calculate the probability density up to that point, this gives you 99.9% of your population. Okay, so this is the link between normal distribution and the 3 sigma rule. And the 3 sigma rule has been applied, and probably already, if you people working in industry, they use this 3 sigma rule in the quality control in what we call the control chart for the mean. Okay, so in these charts, what actually you have, that we have samples from your production line. You calculate in each sample the mean, and then you have like an hypothetical, you have the target mean, and then you have these bands that I show you that are defined in white, and there's 3 sigma limits are put it in this solid red line. So in the quality control scenario, you're going to say that the production is out of control when the average of the production of one sample or more points or more samples, actually they are above or below these 3 sigmas limits. Okay, so then the system should give you an alert and you stop the production line. Okay, so this is more or less the same idea. Of course, in practice, and if you were talking about when you have actually an additional sample from a known seronegative population, actually you don't know what's happening at the population level. Actually, you work with estimates, so you estimate the population mean by the sample mean of the seronegative population, and the standard deviation of the population is you estimate by the standard deviation of your sample. Okay, and then the seronegative rule now is defined in terms of what's happening in your sample. Okay, so in practice, this 3 sigma rule is on the basis of many serological testing out there, and I'm going to give you this is a publication that was published during the pandemics, and then actually they detailed the protocol for serological assay, and they suggested to use the 3 sigma rule to define seronegative, just to define the seropositive cutoff. Okay, and so now I'm going to bring you 2 examples of the 3 sigma that hypothetically that of the 3 sigma rule in 2 studies. One was is a very large study done in the UK, okay, by the National SARS-CoV-2 Serological Assay Evaluation Group, where actually they compare different antibody tests, and this is 5 antibody tests are the Abbott, Diacerin, Oxford, Roche, Siemens. Probably are the ones that are used in Brazil as well. Okay, and what they did is to quantify the specificity of these different antibody assays. Okay, so in this plot, actually they have this screen for a lot of individuals. So you have around maybe 1,000 controls. So people were not infected, okay, by SARS-CoV-2, and they calculated or they estimated the specificity, okay, and for the different antibody tests. I put it here, each dot is the point estimate of this specificity. Then the error bars are the confidence intervals in the 95% confidence interval limits. And the dashed line means the specificity that actually is predicted by the 3 sigma rule based on a normal distribution. And just by looking at this plot, you don't know what was actually the specification of this product, but Abbott, Roche, and Siemens, they actually follow what is expected from the 3 sigma rule. Okay, so the specificity is according to the 3 sigma rule based on a normal distribution. But the Diacerin and Oxford, actually, they don't don't agree with that. Okay, so actually they use a different rule, or they apply the rule in a different way. That I'm going to talk about. So the second example is a data set from Portugal, and actually what they have is they did the same. They try to to estimate specificity of an in-house antibody test, and for that they collected pre-pandemic samples of 216 individuals, and those 216 individuals, they include healthy donors, patients with rheumatoid arthritis, patients with systemic erythematosus lupus. But what it means is that these samples, you expect that these people don't have any antibodies against SARS-CoV-2, okay? And in this protocol, in this in-house protocol, actually they say that they are using the 3 sigma rule to detect, to define seropositivity, okay? So I don't know what was the cutoff in this data set. And here is, on the left-hand side, you can see the data, okay? And the cutoff is actually around 0.4, okay? And so when you apply this cutoff into these pre-pandemic samples, you actually find that after the 212 would be considered seronegative. So it gives you a specificity around 98.2%. So again, so if you actually apply, a statistical test to see if actually the 3 sigma rule holds, which means that the specificity needs to be 99.9, and use the binomial test, actually the p-value is highly, gives you highly significant results. So it means that the specificity of this antibody testing, even that they are using the 3 sigma rule, at least is not based on a normal distribution, okay? And so what's my prediction, according to the, when I estimated the COVID interval for the number of times that was multiplied the standard deviation, it will be around 1.6 to 2.5. So it's far from the 3 sigma rule that you could have, okay? So the conclusion, the first conclusion is that, the specificity of this some serological tests do not fall on this 3 sigma rule based on a normal distribution. And the first thing that I thought about it is like, could be just a question of estimation bias. And because we are talking about estimates, so actually we don't know anything about the statistical properties of the estimators of the cutoff and of the specificity, okay? Like, providing that cutoff. So for that, what I did is just very briefly, the question is exactly this. So the scenario is that if your data is coming from a normal distribution, what's the expected value of your estimated of the cutoff, which means the mean plus 3 times the sample standard deviation. Is this expected value equals to what's happening at the population level? So it means that is equal to the population means plus 3 times the standard deviation at the population level, okay? And the same thing for the specificity. So what is the expected value of your estimator of the specificity? So these things are very easy to calculate. So to evaluating bias of this estimator, very simple. You can decompose the expected value like this. Okay, you have a sum. The cutoff is like a sum, so you can have expected of each factor. The estimator of the population mean is actually unbiased. Everyone knows that. So the sample mean is on average is the expected value is the population mean. But what happens to the expected value of your sample standard deviation? Is it equal to the standard deviation of the population? So first of all, coming back to very basic basic information about estimators of the variance. So here you have the typical estimator of the variance that is divided by n, okay? And everyone knows that the expected value of that estimator is not exactly the variance of the population. You have this factor that is actually giving you that the estimator is biased. So you actually can construct an estimator that is unbiased by multiplying this factor or the inversion of this factor, by this the sample variance, and this gives you this very simple textbook estimator of the variance, when actually you instead of dividing the sum of squares by n, you divide it by n minus 1, and this will give you the expected value of the estimator equal to the the variance of the population. So far, so good. Okay, very simple stuff. Everyone knows this, basic knowledge from textbooks. But we are still not there. So what happens actually to the estimator of the standard deviation? Okay, and then I made some research, and I came across with this paper of Oltzmann from 1950s, published in the American Journal of Psychology, which is interesting because it was not a journal on statistics. And so the standard, so if it actually is showed that this corrected the estimator of the variance is actually, when you square root it, actually this estimator doesn't coincide, is biased in relation to the standard deviation of the population. And here is the factor that is actually leading the bias. Okay, so what it means that actually, because it's just a factor, actually you can construct a corrected version of the standard deviation for a normal distribution. Okay, and this can be done. I'm not going to show you this, but if you use the same thing for the biased estimator of the variance, and you square root it, you are going to have, again, the bias is even greater. Okay. Okay, so evaluating bias. So it means that if you apply the C-Figma rule with a sample mean plus 3 times the standard deviation of your sample, but divided by n, you're going to have bias in your estimator. Okay, so the estimator of the threshold is biased, and as a consequence, the estimator of the expected specificity is also biased. Okay, so but this bias actually explains these differences that I've seen in the data and what is predicted by the 3 sigma rule. And so what I did here is just to have the bias as function of the sample size. So this is the estimator of the sigma. Okay, so the standard deviation, the population standard deviation. Okay, and here is the 2 versions of the estimator. So one is based on on the corrected on the square root of the corrected sample variance, and the other one is a square root of the usual sample variance. So you can see that for the sample sizes below 50, actually the bias is negative. Okay, and when the sample size goes to infinite, the bias is almost negligible. So for example, for this study in Portugal, where actually they used 260 individuals, the bias of the estimator of sigma is negligible. The estimator of the cutoff, again, the bias is also negative. Okay, so you have an underestimation of the cutoff every time that you apply these 2 estimators. But when you apply when you use in a sample size of 216 individuals, again the estimators are approximately unbiased. Okay, here is actually what I put it here is the estimator of the specificity. Okay, and here is not bias that I represented, but this is what is expected from the two estimators, okay? And what you can see is this let's say, like salmon pinkish area. This is the confidence interval, okay? And the two lines is actually, this is what is the expected value of the estimator. So you can see again for this study that the expected mean of the estimator doesn't even is close to the confidence interval obtained for this study. So the conclusion from this part is actually estimation bias cannot explain deviations from the C sigma rule for the normal distribution. So something must be going on with this data. Maybe what's happening is that antibody values of the seronegative population actually should not follow a normal distribution, okay? If they are applying, sorry to come back, if in this example they say that they use the 3 sigma rule, and if you don't get the same specificity as expected by the normal distribution, then the data shouldn't look like normal distribution, okay? So what happens to the 3 sigma rules when applied to the non-normal distribution? And this becomes a little bit more, a little bit more advanced. And if you go back to the probability theory, and I'm not a very theoretical guy, I just use what people already proved. So they have, if you go back to this probability theory, you have this interesting Cantelli-Chebyshev inequality, and they have this probability of the deviations of the mean of the population, okay? And actually you can see that you can bound the probability of the mean plus a certain number, okay? And this is bound by this equation, by this inequality. So what is important to highlight is actually for this inequality to hold, you need to have, well, a finite variance, okay? So finite mean and finite variance, okay? So for example, if we use the Cauchy distribution, this inequality doesn't hold, okay? So the inequality actually is very helpful, because in this inequality, this lambda that you see here, I can replace it by the 3 sigma, okay? And then I can say that what is expected for any distribution, any shape, is that this probability, this quantile here, is actually below 0.1. So it means that the specificity is bounded. So the specificity should be higher than 0.9. So in that case, okay, both examples, they are the specificity of the first example, all the specificities are, above 97.5%, even taking into account with the lower bound of the confidence interval. For the second example, the same. So now you're going back to 95. So the lower bound of the confidence interval is around 95%. Okay. So at least what you kind of say that this Cantelli-Chebyshev inequality at least is a kind of like in agreement with what's happening here. Okay. So the question is, okay, they are not normal distributed. It seems like the specificity is actually the data agrees with this bound. So the question is, what are the candidate probabilities with distributions compatible with this data? Okay, and this came with an interesting exercise. And actually, it's about statistical modeling. So what kind of probability distributions you can think of for the seronegative population? So like until now, I used all the calculations mostly for the normal distribution, and now you can have like different, let's say, generalizations. Let's say one of which is not a generalization, but is a data transformation. So you have a log normal distribution. Okay, so you have, if you log transform, then you're going to have a normal distribution. Okay, then you can think about extension of the normal distributions that consider skewness, okay, and have heavy tails, okay. So for the skewness, you can consider a version of the normal distribution called skew normal distribution, in which you introduce a parameter that actually control the skewness of that distribution. This is this skew normal distribution was proposed by Azzalini, and then other distributions based on the skew normal distribution, arose in the literature. So another extension of the normal distributions is actually considered that you have a generalized T student distribution. In that case, what you have is that the T distribution, the generalized students T distribution, should have heavy tails, okay, but is symmetric, okay, and the degrees of freedom of this distribution, controls the heaviness of the tails or the fatness of the tails, okay. And then you have some kind of a generalization of the most general model they can think of, that is a skew T distribution, when actually you have a degrees of freedom that controls the heaviness of the tail, plus a skewness parameter that controls the skewness of that distribution, okay? And now I'm going to show you just some compatibility of these distributions with the data using the, let's say, the standardized version of these distributions, okay? So let's start with predictions, for the normal distribution. Everyone knows this, again, textbook statistics. Here you go. You have the expected value of random variable x, defined in terms of mu and sigma squared. Okay, and if we use a log normal distribution, that actually the mu and sigma are equal to 0 and 1 respectively, you actually can calculate the expected value and the variance. And if you apply the 3 sigma rule to this case, actually the cutoff is around 8.1. Okay. And then if you calculate what is the cumulative distribution at that cutoff, you're going to see that this quantile, this probability is around 98.2, okay, %. And if you go back to the example 2, this is exactly the specificity that you more or less you get. So the specificity, the point estimate was around 98.2 or 15. And so the predictions of a normal and all normal distributions actually agree what is looking, with this data. Okay. So what happens to the predictions from the generalized T distribution? Okay. So in this case, it's again, like I said, I'm using the standardized version of this distribution. So I only have one parameter varying, which is the degrees of freedom. So in that case, the data, so here is the, again, this pinkish area is the confidence interval. On the x-axis is the degrees of freedom, and on the y-axis is the specificity, using the specificity. And then in blue is actually the probability expected by applying the 3 sigma rule. Okay. So in this case, what is compatible is actually when this blue line, intersects or goes into this, pinkish area. So it means that in this, for the generalized T distribution, if that distribution has degrees of freedom between 3 and 6, the specificity, observed specificity is in agreement with this expected. Okay. What happens for the skew normal distribution? Again, I'm using the standardized version of this distribution, so I'm just varying the skewness parameter. Okay. So negative value of the skewness parameter, it means that there's no left skew. If it's positive, it means that this is right skew. Okay. Again, so this is the if you apply the 3 sigma rule, and this is what they expect the specificity when you apply the 3 sigma rule, and when the blue line goes into this this pink area is actually the skewness parameter compatible with the data is actually positive. So it means that skew normal distribution is also compatible with this data as long as the skewness parameter is positive. Okay. And of course, you can make it even the more general case when actually you have the generalized skewed distribution, and you can see that the skewness parameter is positive and the degrees of freedom can be from 5 to 15. Okay. So almost at the end of my talk, and so the conclusion of this part is that so the seronegative population could be explained by the right skewed and heavy tail distribution. And if you want to make it very simple, a log normal distribution is the best candidate for the example too. Okay. So what is actually the summary of these three stories, or the three parts of this webinar? So first of all is that some of the reported specificities do not follow the 3 sigma rule based on a normal distribution. Current estimators for seropositivity, threshold, and specificity are biased. Okay, mostly they are biased, but they cannot explain the deviation of the sigma rule in the examples that I show you. Okay, so the seronegative population should have a right skew or a heavy tail distribution. Okay, so this is the conclusions. So what happens to this question? The 3 sigma rule, is it a beauty or a beast in serology data analysis? Okay, and from my perspective, it's to answer this question is that in fact the 3 sigma rule is based on beautiful mathematics with nice predictions for the normal distribution. And when you say that you're applying the 3 sigma rule based on a normal distribution, what actually you're doing is control for specificity. Okay. The problem is when actually the data is not normal. Okay, so when you apply the 3 sigma rule when the data is not normal, so what I say is anything goes in terms of specificity. So one study applies the 3 sigma rule, another study applies the 3 sigma rule. If they are not normal, the data is not normal distribution, the studies are not comparable because they might have different specificity. But if you control for the specificity, then it will be different. So what it means that when you apply the 3 sigma rule blindly, there is a reduction in the comparability among serological studies. Like I show you, for example, in a comparison of these different antibody tests. So what I think is that what we should have is that some kind of renaming of this rule. So if the 3 sigma rule applies, or you have a way to transform the data that looks like normal, then you can apply Lilly Ford, Anderson, Darling, Shapiro Wilkes just to check if the data looks like normal. If it doesn't look like normal, so what's going to happen to specificity? And for that, I think the 3 sigma rule is much more informative when actually you put it in terms of quantiles. And this quantile is the quantile 99.9%. So what I see is that instead of calling this rule 3 sigma rule, it should be called Q99 standard or 99 QR. And as a joke, I put it almost certain rule. Okay. And what is interesting is that old stuff comes new. And when I was preparing this talk, I found out that on Wikipedia, when this 3 sigma rule was applied to control charts, so it means in quality control, Egan Pearson suggested to replace the 3 sigma limits by the percentiles of the normal distributions. Okay, because if the normal distribution doesn't hold this, but if you always go into the percentiles or the quantile that you always think of, the specificity is always controlled. So the studies are comparable. Okay. So this is what I wanted to show you today. I hope I didn't take a lot of time. And I would like to acknowledge people from my research group for listening, for giving comments about this presentation. I also would like to thank people from the Center of Statistics of the University of Lisbon, especially Giovanni, that suggested my name for your seminar series. My host at Warsaw University of Technology, especially to Przemek Biesek and Mustafa Kavus. Of course, Michel Montoril for inviting me. And lastly, I would like to acknowledge the funding from the Fundação para a Ciência e Tecnologia of Portugal and the Polish National Agency for Academic Exchange that is supporting my visit in Poland. And I hope you enjoy it, and I open the floor for questions, and thank you very much for listening.
Thank you, Nuno. It was a nice talk.
Should I stop the presentation, or how do you want to do it?
Feel free to stop for now. If somebody have some question, you can open it again.
Okay. Just stop presenting.
I have a curiosity.
Yes.
I'm sorry?
Do you still see my presentation? No.
No, not anymore.
Okay. Thank you.
Okay. I have a curiosity just, but I would like to open for questions now. If somebody in the audience want to make any question, to ask any question, feel free right now. No questions?
Even in Portuguese, don't worry.
Even in Português.
Nuno.
Oi, Vaira, tudo bem?
Quanto tempo?
Tudo bem.
Como estás?
Eu também esqueci, fui a Maringá, fui com Maringá a convite da Vera.
Pois é, viu?
Foi a Rebras.
Isso, é Rebras. Não, e o Michel me explicando para mim quem era você. Eu disse assim, mas eu conheço o Nuno faz muitos anos. Que bom que você aceitou o convite. Na verdade, eu estava um pouquinho por fora de quem era o palestrante. Quando eu olhei, eu estava numa reunião, eu digo, não, eu preciso entrar. Entrei meio atrasada, mas para dizer um oi para você. Mas ainda deu para pegar um pouquinho do que você estava falando. Achei super interessante a ideia da apresentação. A minha pergunta é, você chegou a fazer essa comparação dessa abordagem sua com alguma abordagem paramétrica para ter uma noção de que o que você está fazendo realmente é uma boa escolha? Que eu achei muito interessante, muito simples assim, a ideia do 3 sigma.
Sim, exatamente. O problema que eu vejo, isto aqui tem a ver com um bocadinho com a minha investigação que eu estava a fazer na London School of Hygiene and Tropical Medicine, é que, principalmente em malária, a população seronegativa é muito difícil de encontrar. E então estima-se. E a partir daí, se a distribuição de base da população seronegativa não é normal, uma pessoa não sabe qual é a especificidade dessa população. E depois, quando começa-se a comparar, a dizer se este país está em eliminação ou se tem uma diminuição da infecção, não se consegue dizer nada porque a distribuição de base não é normal. Pelo que eu sei, se é isso que se me estás a perguntar, eu aqui nestes 2 exemplos, isto são exemplos sem dados originais, não é?
Não tem dados originais, esse aí é simulados.
Não, isto
mesmo.
É exatamente os dados que foram publicados e têm a especificidade estimada, só, apenas.
Tá. Uhum.
Tá bem? E por isso foi só uma demonstração que, quando as pessoas falam em 3 sigma, ninguém sabe o que é que fala. Agora, tendo os dados por base, o que tenho visto é que a população seronegativa ou segue uma distribuição log normal, ou seja, transforma-se os dados em uma escala log, ou então, mesmo às vezes em escala log, tem que se utilizar a Skew normal. Ou seja, tem que haver... o melhor modelo paramétrico que eu tenho visto por aí são modelos em escala log e ainda são assimétricos.
Exatamente, por isso que eu perguntei.
O skew normal. O skew normal, nós falámos... Eu tenho um artigo com um dos meus estudantes de doutoramento, o Tiago Domingos, em que exatamente a gente propõe este tipo de modelos para este tipo de dados, ou estes modelos assimétricos. Porque mesmo após a transformação de dados, a população seronegativa não é bem captada por uma distribuição logo normal, em algumas aplicações. E o melhor modelo é o skew normal, pelo que nós conseguimos modelar. Mas exatamente, se tu aplicares o 3 sigma numa distribuição skew normal, tu não sabes qual é a especificidade que vais obter no final, porque tudo depende dos parâmetros da simetria.
Isso é verdade, isso é verdade.
Por isso é que eu estou a dizer que a mensagem aqui é: se nós aplicarmos modelos paramétricos, diferentes de modelos paramétricos, mas sempre escolhermos o mesmo percentil da distribuição, os estudos passam a ser comparáveis. Agora, se nós não controlamos isso e aplicamos a regra só por 3 sigma, a gente não controla isso.
Tá. Deu para entender. Muito interessante. Achei super, assim, de uma maneira muito simples, uma abordagem interessante, né? Eu gostei bastante.
E o que é interessante é que são resultados que a maior parte das pessoas sabe, não é? Só que quando aplica, principalmente na parte do estimador da variância, né? Uma pessoa não pensa no estimador do erro padrão, do desvio padrão.
Não.
Se é enviesado ou não. Né? Agora, em casos de grandes amostras, não há grande diferença. Nós podemos usar qualquer estimador, não é? Mas eu nem fiz os cálculos em relação, sei lá, erro quadrático médio. Eu nem fiz esses cálculos, mas pelo menos em termos de bias eu não posso invocar isso, né? Pelo menos
Muito
para grandes amostras os estimadores mais ou menos são comparáveis.
Maravilha. Valeu, muito obrigada.
Obrigado,
Passo a palavra aí para o próximo que levantou a mão. Prazer em vê-lo.
Fernando?
Oi, boa tarde, Nuno. Obrigado pela apresentação, achei bem interessante, bem rica. Apesar da simplicidade, eu nunca tinha pensado realmente no viés que a gente tem no estimador do desvio padrão. Eu acho que nem nas aulas de graduação, no mestrado, a gente toca nisso, mas achei bem. Mas a minha pergunta vai mais no sentido prático, porque eu acho que na bioestatística, né, na área de medicina, a gente vive se debatendo sobre essas questões de pontos de corte, não só em soroprevalência, mas é que você chamou a atenção, eu até levantei a mão porque você chamou a atenção para um ponto, que eu fiquei curioso em saber qual que é o impacto disso, dependendo, inclusive, do tipo de vírus que está sendo estudado, porque você fez os seus exemplos todos em cima do SARS-CoV-2, né? Mas você citou na malária, que é algo um pouco mais difícil de ser detectado, né? E eu imagino que em algumas outras doenças negligenciadas isso também ocorra. A gente está tendo aqui vários problemas no Brasil, inclusive, com essa questão toda de tuberculose.
Sim, dengue,
né? Dengue, exatamente.
Zika,
né?
chikungunya.
Zika, chikungunya. Então, primeiro, esse ponto, se isso é muito dependente, né, do tipo de sorologia que está sendo feito, e se você progrediu ou fez algum tipo de simulação, ou se é possível, com esses resultados que você tirou, para tentar ver qual que é o impacto disso em um estudo de soroprevalência, por exemplo. Porque aqui no Brasil, a gente começou no início da pandemia, né, um grande estudo de soroprevalência que acabou sendo descontinuado, infelizmente, mas que eles usam aquele kit já pronto, que já vem com esse ponto de corte, eu imagino, pré-especificado. Então, qual que seria o impacto, por exemplo, dessas suposições, né, em um estudo de soroprevalência?
Sim, eu vou... Para responder primeiro a esta segunda parte, que é... Eu não fiz o estudo, esse estudo, mas não é preciso fazer esse estudo, porque o que é importante é que quando, supostamente, um kit sorológico tem o ponto de corte, mas o que o fabricante deveria também incluir era a especificidade. Porque quando se faz o estudo de seroprevalência, não é? ou um sero epidemiológico, há estimadores que corrigem para a especificidade e a sensitividade do teste. E é um estimador chamado Rongen qualquer coisa. Agora não me estou a lembrar. Ou seja, se mesmo que a gente não... Pronto, fazer a análise dos dados um bocadinho às cegas, mas tiver a informação do fabricante, qual é que é a especificidade e a sensitividade do teste de anticorpo, aí nós podemos corrigir a seroprevalência empírica, digamos, baseado naquele ponto de corte, e corrigi-la para esta sensitividade e especificidade, para criar, no fundo, no final, digamos, a seroprevalência, digamos, verdadeira. Não é? Tu estás a perceber a minha ideia?
Isso, inclusive, foi uma coisa muito criticada, porque no começo, inclusive, desses estudos no Brasil da SARS-CoV, a especificidade era muito baixa ainda, né? Isso era início dos anos, né, de 2020, então foi uma das críticas, inclusive, que o estudo recebeu no Brasil. Acho que era uma especificidade de 70%, algo que era, assim, bastante complicado de se trabalhar, né?
Pois, mas à partida, é assim, à partida, pelo menos dá para corrigir os estimadores da seroprevalência se tiver a sensitividade e a especificidade. O problema é que eles metem lá o cutoff e a gente não sabe qual é que é, o que é que se está a fazer, não é? E isso é que é verdadeiramente o problema. Em relação à primeira parte da tua questão aqui os kits serológicos, no fundo, os dados mais bonitos que a gente poderia ter, não era ter uma população aqui, outra população aqui e o ponto de corte cá no meio, bem distanciado, não é? Algumas infecções, principalmente aquelas que têm uma resposta imunitária muito aguda, não é? Muito forte, vai-se ter essa resolução de anticorpos. Agora, por exemplo, no caso de malária, chikungunya, dengue, com o problema de reatividade cruzada dos anticorpos, pode haver sobreposição entre a população seronegativa e a seropositiva. Por isso, eu aqui nesta apresentação parti de base em que existe uma amostra externa em que se faz a estimação da especificidade e do ponto de corte. Mas para doenças tropicais, como o chikungunya, o dengue e o Zika, normalmente não há anticorpos de produção massiva, né? Então são os próprios laboratórios a fazer este estudo. Estás a perceber? E por isso, às vezes, os kits não estão optimizados. E por isso, entra-se na estimação do ponto de corte quando há um overlap. E isso ainda torna a coisa muito mais complicada.
Sem dúvida, sem dúvida. Ok, muito obrigado. Muito
obrigado,
interessante.
Alguém mais tem alguma outra pergunta, algum comentário? Excelente. Então, mais uma vez, né, obrigado, Nuno. A Verita quer fazer um comentário, Vera?
Bater palma, né?
Obrigado, Vera.
Vamos, por gentileza, abrir os microfones para aplaudir